Welcome to Maths with EJD. We continue with the numerical analysis playlist. And of course, we've been considering numerical solution to initial value and boundary value problems for ordinary differential equations. And so far, we've looked at solutions, numerical solutions to initial value problems using both using Euler method and Runge-Kutta method. At this point, I want to take a pause and consider stability and convergence analysis for those numerical methods. And afterwards, we'll continue with methods for boundary value problems like finite difference method and shooting method. So let's see how this goes. So now we're talking about stability and convergence analysis. Okay. Um, let's see an overview. It is important to understand how to analyze the stability and accuracy of numerical methods for solving ordinary differential equations. That's ODEs for short. This involves this involves ensuring the numerical solution avoids the growth of errors, over time, which the growth of errors over time, which would destabilize the solution. Okay, so let's go ahead and talk about uh, Euler's method stability condition. Euler's method stability condition. So consider the first order linear ordinary differential equation, which is y prime equals lambda y prime equals lambda y. We can actually rewrite this as dy dx equals lambda y. And of course, that's more like saying that okay, we can say that is actually the same thing as f of x comma y, right? Because that's the general way to write this kind of equation when you have dy dx equals lambda y. So this expression here now is a function of both x and y. That's usually what it should be. So here we say where lambda is a constant. Lambda is a constant. Okay. So Euler's method approximates the solution using the formula yn plus 1. We've used this in the past already. Yn plus 1 equals yn plus h lambda yn. Because basically, lambda yn is supposed to be f of, let me even do it that way. So this should actually be h, all right, f of x and yn, if I might put it that way. So we have yn plus 1 equals yn plus h of f of, now in this case, now f of x and yn is, f of xy is lambda y. So that means we have that to be lambda yn. So that's what we definitely have there. So see what happens now. For this method to be stable, for this method to be stable, the numerical error must not grow exponentially. So the stability condition for Euler's method is given by the absolute value of 1 plus h lambda less than 1. So if this condition can be met, then we can say that the stability condition is, we can say that the solution is stable. So here, where h is the step size, as we already know, h is the step size. So if this condition holds, the numerical errors will remain bounded, ensuring stability of the method, So let's take about 2 examples to see how this goes. So let's say example 1 now. Example 1. So investigate the Euler stability condition for y prime equals minus 5y with h equals 0.1. Okay. Now, one point we need to note from here is the fact that this lambda we have here is basically the same thing as partial f, partial y. That's really important. It's partial f, partial y. That's if we differentiate f with respect to y, you get lambda. So that's useful for what we have to do next. So if I go back here and say something like this, you know, we won't bother applying the Euler's method. We just go straight to investigate the stability condition check. So using the formula, for Euler's method stability, Euler's method stability, we have the absolute value of 1 plus h lambda less than 1. So let's see if that works for this particular system we have now. This is the condition now. Okay. So here, lambda is equal to partial f. So the function we have in this case, right, is minus 5y. So, just like we said, if I'm going to write what we have, that's y prime, right? Y prime is equal to f of x, y, which is equal to minus 5 lambda. Okay. So you discover that lambda itself is partial f, partial. No, this is minus 5y. Yeah, it's minus 5y. Sorry. I was wondering why I'm calling that lambda. So this is minus 5y. Minus 5y. Okay. So partial f partial y now is equal to minus 5. So we have lambda to be minus 5. settled. And then what else do we need? We need h. H is already given. H is 0.1. So the absolute value of 1 plus h lambda would be equal to absolute value of 1 plus h is 0.1. Lambda is minus 5. Lambda is minus 5. Okay. So we have this to be absolute value of 1 plus 0.1 times minus 5. That's minus 0.5. Okay. So that's like 1 minus 0.5. That is absolute value of 0.5. So with that, we have 0.5. So what that simply tells us is that the absolute value of 1 plus h lambda is equal to 0.5. And that's clearly less than 1. Okay, that's surely less than 1. So then we can say that since 0.5 is less than 1, the stability condition for this equation, is stable, and the errors will not grow exponentially, The solution will decay. Smoothly as expected. Okay, I mean, that's one example. Let's look at another example that may not be exactly like that. So check Euler stability condition for y prime equals x plus y with h equals 0.1. Okay, so for the solution, we have y prime equals f of x comma y equals x plus y. So we know the condition, the Euler condition is that the absolute value of 1 plus h lambda is less than 1. So that's what we want to check for this solution right now. And from all we have, right, we know lambda. To get lambda, we need to differentiate the function f with respect to y. So we can say that lambda is equal to partial f of x comma y partial y. And since partial f of x comma y is x plus y, so that means lambda is going to be equal to 1. So we have lambda to be equal to 1 easily. And then, of course, we have h given us already to be 0.1. So h is 0.1. So with those, we can continue. We can then say that the absolute value of 1 plus h lambda is equal to absolute value of 1 plus h is 0.1 and lambda is 1. So that we now have absolute value of 1 plus 0.1. So that is equal to absolute value of 1.1. And that is simply 1.1. So that is greater than 1 actually, but the condition states that it should be less than 1. So we have the opposite of what we really want in this situation. So since 1.1 is greater than 1, the stability condition is not satisfied. For this equation. This means Euler's method will likely lead to an unstable solution. With errors that grow exponentially over time. And that's how that is. So we see that in the case of y prime equals minus 5y, Euler's method is stable and provides the correct approximation as the solution decays exponentially. The stability condition holds, and the numerical errors do not grow exponentially, leading to a smooth decay of the solution. However, for y prime equals x plus y, which we just did, right, the stability condition fails because the absolute value of 1 plus h lambda is equal to 1.1, which is greater than 1. So as a result, Euler's method will not give a stable solution. In this case, so we can say that in this case, right, in this case we just did, in this case, more advanced methods like Runge-Kutta, say RK4, would provide better stability and accuracy. Better stability and accuracy. Of course, we solved this second problem using both Euler's method and Runge-Kutta method in previous videos, and we discovered that actually for Euler's method, the solution decays as we keep going, as we keep increasing the iteration, right? The result begins to divert from the exact solution. So, all right, so let's look at some key takeaways before we leave this. Key takeaways. So first of all, Euler's method is simple to implement, but not always, but may not always be stable, may not always be stable. We have that, and then we can also have this second point that the stability condition, absolute value of 1 plus h lambda less than 1 must be satisfied for stability. That goes. Then we have this other point 3, that for equations like y prime equals minus 5y, Euler's method is stable and accurate for reasonably small step sizes. Okay, then we also have number 4 for equations like y prime equals x plus y. Euler's method may be unstable, and more advanced methods like Runge-Kutta are recommended for stability. And finally, we have the 5th point. The stability of Euler's method depends on the step size, depends on the step size and the properties of the equation being solved. So with this, we come to the end of this video. If you have subscribed, thanks a lot. If you have not, go ahead and do that because there's a lot more coming. So hit the notification bell also so you can always get alerted time a new video is released. Also, comment, let me know how helpful these videos are, and let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Watch out for numerical solutions for boundary value problems in the next two videos. Bye.